Hello everyone and welcome to chapter 26.3, and this is where we're going to learn about the life cycle of stars. So just like with people, stars actually go through a life cycle with a birth, a life, and a death. And different types of stars will have very different lives. So we talked about how to classify stars in the last section, and we talked about classifying stars by temperature or color that they give off, by their chemical composition, by their apparent brightness, compared to where we are, and all of those determine what kind of star we're looking at. So dwarves and supergiants will have very different final stages in their life cycles as stars, and red stars and white stars will have different life cycles because of their different temperatures. So while all stars go through a life cycle, their life cycles are very different depending on what kind of star they are. So stars have a birth, and they form from large clouds of dust and gas called a nebula. Now this may sound strange because when we think about space, we usually think about it as being a vacuum, as being very empty. But there are some places in space that aren't completely empty. They actually have a little bit of hydrogen gas and a little bit of hydrogen dust and other things floating around in there. It's just that it's very, 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 very spread out. But because that dust and that gas has mass, they're made of atoms, so they have mass, they have a gravitational attraction to each other. And eventually, that cloud, that nebula, will collapse in on itself due to its own gravity. All those little particles start drawing closer and closer and closer to each other. And once the particles get tightly packed enough that fusion begins, in that it gets hot enough that the hydrogen atoms will collide to produce helium. This is the beginning stages of a baby star. And the baby star is called a protostar. So you can see in this picture right here that this glowing cloud of dust is the nebula. Now, if we were to look at a nebula with a regular telescope or our naked eye, we would not see it this color. This image is taken with an infrared camera. Remember, we talked about infrared is before red light, and then it goes up through the rainbow to violet. So infrared is an energy of light that's lower than red. And by using an infrared telescope, we can actually see this low energy light in here. You can see these two bright little dots. Those are the beginnings of protostars. Those are clumps of dust that have come together enough that fusion has actually turned on. Now, once fusion begins, we now have this balance of the outward pressure from fusion and the inward draw of gravity. And once that stabilizes, once the outward push is equal to the inward pull, the star has reached its adulthood. Basically, it's gone through puberty and it is now on its way as an adult. And it turns out that most stars spend 90% of their lives on the main sequence of the HR diagram, and a star's mass will determine its place. So a very, very, very massive star will be found somewhere up here and will most likely be very, very hot, and it will be in the blue region of stars. A lower mass star will be somewhere down here and will most likely be red and a lower temperature. Our sun is a medium-sized star, and it is a medium energy, a medium temperature, so it lets off yellow light. Now, a star's life cycle will actually follow this diagram, which is pretty interesting. What happens is as the star moves past the protostar stage and moves into its place on the main sequence, let's say it's our sun, it will stay there for 90% of its life. But once it starts to die, it will actually expand in size because the outward push of fusion, making those heavier elements, is greater than the inward pull of gravity, and eventually it will become a very large star, either a giant or a supergiant. In the case of our sun, it's going to become a red giant. As it expands, it's going to cool off, and it will become very, very large. Now, once it's reached a certain point, it can no longer sustain its own fusion. It's basically burned up all of its fuel. Once that happens, it's going to shed its outer layers, losing a whole bunch of weight, until the only thing that's left is a white dwarf. So, any star, including our sun, is going to follow a sequence just like this on the HR diagram. But for 90% of its life, it's going to be found right on this line on the main sequence. Now, like I said, once stars use up most of their hydrogen in their core, they can't go through the process of fusion as much anymore, and they begin to die. And the type of death really depends on the star's mass when this occurs. A star can either end up as a white dwarf, like I just said, as a neutron star, which is a pretty strange thing, or a black hole. Low and medium mass stars, like our sun, will become white dwarfs. After they expand into their big red giant stage, they're going through their midlife crisis, they will start to collapse under their own gravity because they can no longer sustain fusion. The outer layers of that star are then shed, and they're shed to create a nebula. So that's where all of the dust and gas comes from to form new stars, is from dying stars. Those dying stars shed their outer layers, which exist as these clouds in space, and then those clouds can then come together in different ways to make new stars many, many millions of years in the future. But after the outer layers are shed, the only thing that's left is the very, very, very hot core of what was that star. And that's what's all that's left of that star at that point, and we would now consider it a white dwarf. Now, the high mass stars are the really exciting ones when they die. They do expand, and they expand to become supergiants, but it turns out that they use fusion to make these really, really heavy elements, up to the elements like iron. And that really, really hot fusion makes the mass of the star get used up very, very quickly. It turns out that really large stars, high mass stars, die a lot faster than the small ones because they burn through their own fuel more quickly. Now, these high mass stars, because they're burning through their fuel so quickly, can't actually overcome the pull of their own gravity, and they collapse so quickly and violently that when this collapse happens, it creates a supernova. And a supernova is a giant explosion. So a supernova is an explosion so violent that the dying star becomes more brilliant than the entire galaxy. It lets off so much heat and light all in one go that we get all of our heavy elements like gold and silver and palladium from these gigantic explosions. And once this explosion happens and the outer layers are removed, the core will continue to collapse in on itself because it's so heavy. The high mass stars that are about 3 times the size of our sun will turn into a neutron star. And a neutron star is kind of like a white dwarf, except it has way, way, way more mass, and it's so hot that it gives off radiation in the form of these beams. This is also known as a pulsar, because if you can imagine these beams as being a flashlight, and the Earth is somewhere over here, as it spins around, this beam will hit us and then we'll move away. And then this beam will hit us and then move away. And it looks like the star is pulsing based on where that radiation is pointed as it spins, and that's why it's called a pulsar. Now, these things are huge. They are gigantic. It turns out that a spoonful of a neutron star would weigh nearly 1 billion tons when on the Earth's surface, when interacting with the Earth's gravitational field. 1 billion tons inside 1 teaspoon of matter. That's how much mass is in these stars. Now, if that's not crazy enough, if a star has even more mass than 3 times our sun, it will collapse so much that it will turn into a black hole. And on a basic level, a black hole is where all matter collapses into a singularity. And a singularity is 1 point in space. It's not even considered 3-dimensional, it's considered 1-dimensional. Or, I'm sorry, 0-dimensional. It is a single point in space. And it has an infinite amount of mass in it. All of the mass that was in that star's core collapses to a point that is nothing, basically. And this seems really counterintuitive, but we're going to talk more about black holes in a little bit. But basically what this means is when this really, really massive, incredibly massive point in the middle of space interacts with any other thing in the universe, whether it has mass or not, the gravitational pull is so strong that it pulls everything toward it, and eventually things cannot escape its gravitational pull. So just like on Earth, when we shoot a rocket into space, eventually, once the rocket goes far enough, we can get out of the reach of Earth's gravitational pull, because the farther away from an object you are, the weaker the gravity. A black hole can suck basically anything into it as long as it's within what we call the radius. And it's really crazy. It even does this with light, and light doesn't even have mass. So, black holes are these really crazy things, and we can talk about them more in class. I actually have a whole day set aside for us to just talk about how weird black holes are and how weird the universe is. But they do exist in space, they are real, and they're made by high mass stars dying and collapsing in on themselves. So I hope you liked that discussion of mostly star life and star death, and here is your homework. Please finish these for tomorrow.